brief thought about the causal inference, and then as Thomas mentioned, the causal inference actually cause effect originally probably can trace back to the philosophy. So I want to invite the Zhang Kong to give a remark probably from the computer science aspect and also from the philosophy aspect, because Dr. Zhang is also at the Department of Philosophy at the College of Management Universities. Okay. Kong?
Yeah. Hey. Thank you very much, Professor Zhou, for the hello. Can you hear me?
Yeah. Yes, we can hear you.
Okay. Cool. Yeah. For the introduction and for making this conference happen, and thank you very much, Thomas, for the very brief but exciting remarks on causal inference in statistics. So in this part, let me just quickly share something about the connection between causal learning, including causal structure learning and causal representation learning, and machine learning. So let me just give some examples, which are typical machine learning examples. So in many cases, as you can see from those pictures, so we have some data in our experience, right? We want to learn something, learn a model, and make prediction in a new scenario, right? It's known as either domain adaptation or transfer learning or domain generalization. Although there are subtle difference between the concept here, basically we try to do well in a new scenario, in a new distribution. So in order to solve this problem, clearly you can see we would like to see to learn and make use of some kind of representation of the distribution changes, right? So that we can really adapt to the new environment. And in the second example, so essentially this is the AI diagnosis system. If AI system says something about the disease, then furthermore, we would like to see what causes the disease and how to treat it, right? So we would like to see some explainability of the disease, of the diagnosis process. So in the third example, basically it's a recommended system. So once you receive some recommendations, probably you would like to see why a particular item was recommended, right? Because probably the reason why it's recommended is kind of not valid. So you want to understand why. And at the bottom, I gave another example. In deep learning now, almost everyone in deep learning knows this problem. It's essentially known as the adversarial attack problem. And because of this, we say deep learning suffers from adversarial vulnerability. So on the very left, you can see a picture of panda. Then both human beings and machines will say, oh, this is panda. But if you add noise to this picture, noise of particular pattern to this picture, or change particular pixels in a specific way, then machines will say, oh, it's something different. But for us, clearly it's the same thing, right? So what causes the difference? Essentially, mathematically, you can prove that as long as machines and human beings learn and make use of different high-level feature representations, then there's always the adversarial attack problem, because you can always tune the input so that either the machines or human beings make different decisions, right? So as long as our decisions and the machine decisions are not consistent, we say it's the adversarial attack problem. Then the problem is how we can avoid this issue, right? Essentially, we want to make sure that the machines and human beings are on the same page. If there are no misunderstanding, then we can rely on the machines, right, to make decisions. Then the next question would be, what kind of feature representations we make use of as human beings, right? Okay, so as Thomas just explained, essentially there's a big difference between association and causality or causal representation. I will skip this because I suppose, Thomas already talked about this part. Now, why do we learn causal representation and causal structure? First of all, as you can see from those machine learning problems, probably you want to benefit some downstream tasks like prediction, right? And you believe this representation will be kind of stable, informative, and easy to adapt to a new environment. And in many cases, you want to give the Y-type explanations. And let's try to give a more fundamental answer to this question. So why do we need causal representations? Or why do we learn the causal representation? Some people may say, oh, the external world is causal, right? As a consequence, I should try to recover the property of the true causal process. That's good, but some other people may say, oh, how can I believe that the world is generated causally, right? So here you may give a philosophical argument. As Professor Zhou said at the beginning, I learned this from Professor Clark Glimmer. So basically, he's a philosopher. I'm trying to be a philosopher. So here, you can on the right, you can see Kant's metaphysics. Essentially, what we have or what we can perceive is the world of experience. The world of experience is not necessarily the world in itself. It's actually produced by world in itself and the pure forms of experience. So essentially, this is about our perceptual system. Whenever we see something or we feel something in the world of experience, it's generated by world in itself, but at the same time, our perceptual system automatically enforces some forms, including the concept of space, the concept of time, and the causal order, and so on. So that means our data is basically, our data always has a space, time, and causal order built in. Now, in order to make sure machines and human beings are on the same page, clearly we would like machines to learn the same representations, right? If machines and human beings can learn and use the same set of representations, then we can trust them. Our decision process can be consistent. Now, the question is how we can learn causal structure or causal representations. Essentially, the task is how to find a causal structure with or without latent variables from observational data. And with the causal representation learning, usually we highlight the issue that in real world, usually we have to find high-level hidden variables, and usually the number of hidden variables is smaller than the number of the observed variables in order to understand what's going on. And we can consider this problem, the problem of causal discovery or causal representation learning, basically from this perspective, right? We consider three axes of the problem. First of all, what kind of data do we have, right? In some situations, we have i.i.d. data, independent and identically distributed data. And in some cases, we have non-i.i.d. data. And by non-i.i.d. data, you may have non-independent but identically distributed data, like regular time series, or you may have independent but non-identically distributed data, like non-stationary data or data collected under different conditions. The second axis is whether we can benefit from some parametric constraints on the causal influence or the causal mechanisms. And the last one is whether you allow latent compounders in the causal process. Here, actually, this is a quite quick summary of the recent advances in causal representation learning or causal structure learning. You can see in each setting, depending on whether you have i.i.d. data, whether you have parametric constraints, and whether you allow latent compounders, on the right, you can see what you can get. Clearly, causal discovery or causal representation learning will benefit from the violation of the i.i.d. constraint. Why? Because essentially, in some way, causal modeling and the distribution shift, together with temporal information, are heavily coupled, right? Temporal information and the distribution shift can tell us how the causal models look. Okay, I'll skip this. Here, let me just give some quick examples. This is an archaeology example. So the data were collected by my collaborator, Marlene Novak. So here, she collected 250 skeletons, and she measured 8 variables because in archaeology, they try to understand why people in different areas look different. So here we have a single distribution. In other words, we have i.i.d. data generated by this single distribution. And we don't have parametric constraints because the relationship among those features could be very complex. The features include sex, location, geographical location, diet, cranial size, cranial shape, and so on. So the relation can be very nonlinear. And here, you may use some method to allow latent compounders, or you might just exclude the latent compounders. Here you can see the result by a kind of very popular and early method called the PC algorithm. So you can see from with this algorithm on the data, we know that the geodistance causes the climate, gender causes the cranial size, climate causes cranial shape differentiation, and so on. So it's nice to really see the relations by analyzing the data. You know, data will not lie. If data lies, basically there are some we just ignored some or overlooked some factors in the data, right? Once you model the process correctly, the data does not lie, and you can recover the truth. And of course, in some situations, the essential information you want to recover may be lost in the data. So in that case, right, you can just say, oh, in this kind of data, we may not be able to recover what we want to see. And this is the second example. So across many fields, actually, this is a very important problem, especially in psychological studies. So we have answer scores, and we don't believe that the answer scores are causally related, although they are correlated or they are dependent, right? So usually we say those measured variables were generated by some latent variables, and the latent variables can be causally related. For instance, the answer scores were generated by the underlying mental conditions, and the mental conditions are causally related, right? So the problem is how we can analyze the measured variables to recover the whole hidden world, so including hidden variables and their relations. And here you can see the application of some of the methods we developed in the past years. So this is the t-shirt burnout data. You have 28 variables, and on the right, you can see the hypothesized model by experts. And right here, with some method that we developed, essentially we can recover the same set of latent variables and the same kind of causal ordering among the latent variables. So it's nice because it illustrates two things. First of all, the hypothesized model by experts is very nice because it's really consistent with the data. And the second of all, computational method could be very useful if you want to go beyond the data, as you can see from this example. And you can go further. For instance, in this work, you can just estimate the multiple layers of the latent variables by analyzing only the measured variables, xi's. So essentially, you can allow a lot of latent variables, and you can recover the latent variables across different layers. Essentially, it's a way to illustrate why deep learning is essential. Because if you care about the true causal process, in many cases, you can recover, you can verify that or the generating process actually is layer by layer. It's a deep structure. And now let me give some last examples. So in this scenario, we can just estimate the latent causal processes or latent causal dynamics from video data. This is basically a way to understand the video data. On the left, you can see the first example is known as the kitty mask data set. So and with some recently developed method for causal representation learning from time series data, you can see we recovered the 3 latent processes. Turns out that they are very meaningful. The first one corresponds to the movement in one direction. The second one is the movement in the second direction. And the third one is the size of the mask, right? It's clearly interpretable. And we just took the image data as input. And in the second example, as you can see from here, so essentially the video of 5 balls in different colors. Between some of the balls, there are hidden spring. They're hidden spring, so that's why they are related. And from this video dataset, we recovered 10 latent processes. Turns out that they are just the X and Y coordinates of the 5 balls. So essentially, you recover the balls together with their relations because there could be a hidden spring between some of the balls. So from the video data, you can really see the underlying meaningful objects and their relations. And this is clearly, benefits. This is basically, as you can see from this example, we can really benefit from causal principles applied to those real problems. To summarize, a number of machine learning problems involve suitable representations of the data. So that include domain adaptation and generalization, reinforcement learning, which is essentially a causal problem, recommender systems, which is clearly a causal problem because you want to change the user behavior, trustworthy AI, explainable AI, fairness in machine learning, and so on. So in those things, we have to care about how to represent data or how to extract the information in the data so that we can achieve our goal. And it seems that the causal representation learning or pseudo-causal representation learning provides a very nice way to find the right set of representations from data. And here by pseudo-causal representation learning, I mean, in many cases, we may not make very strong assumptions to guarantee that the learned representation is necessarily causal, but it enjoys some properties like minimal changes. And the last point is that learning and using causality might be one of the components in a higher level AI. There could be other components, but the ability to learn and make use of causality might be very essential when we achieve another level of AI. Okay, thank you very much. And I'm looking forward to the very exciting conference. Thank you.